Hello everyone and welcome. Today, we're diving into a key concept in C# and object-oriented programming, interfaces, and specifically how classes implement them, looking at both implicit and explicit implementations. This is crucial for writing flexible and maintainable code. Let's get started with our iShape example. In this exercise, we'll explore a scenario with two interfaces, iShape and iShapeMer2. Both of these interfaces will define the same set of methods, draw and resize. We'll see how a circle class implements iShape in a straightforward way, and then how a square class tackles implementing both iShape and iShape2 using a technique called explicit interface implementation. This is often necessary when method names collide or you want more control over your class's API. We'll then see how to call these methods and what happens when we try different approaches. Alright, let's look at our first piece of code. Here we define two interfaces, iShape and iShape2. Internal interface iShape. This interface declares two methods, voidDraw and voidResize. Any class that wants to be an iShape must provide an implementation for these two methods. Think of an interface as a contract. Internal interface iShapeMer2. This second interface, interestingly, also declares voidDraw and voidResize. The key point here is the name collision. Both interfaces have methods with the exact same signatures. This presents a challenge. If a class implements both, how does it distinguish which draw or resize it's implementing, or can it provide different implementations for each? This is where the concept of explicit implementation will become very important. Next up, we have the circle class. Internal class circle iShape means our circle class is promising to fulfill the iShape contract. It does this by providing public void draw and public void resize methods. Draw simply writes drawing a circle. To the console, resize writes resizing a circle. This is implicit interface implementation. The methods are public and directly part of the circle class's public API. You can call them on a circle object directly, like myCircle.draw, or if you have an iShape reference pointing to a circle object, like iShapeShape equal myCircle. Shape.draw. This is the most common and straightforward way to implement an interface when there are no ambiguities. Now things get more interesting with the square class. Internal class square, iShape2 means square is taking on the responsibility of implementing both iShape and iShape2. Look closely at how it implements the methods for iShapeMer2, void iShapeMer2.draw, throw new not implemented exception, void iShape2.resize, throw new not implemented exception. This is explicit interface implementation. Notice the iShapeMer2 prefix before the method name. Why use this? Name conflict resolution. We have draw in both iShape and iShapeMer2. Explicit implementation allows Square to provide distinct implementations for each, different behaviors. As you can see, the draw and resize for iShape2 are intentionally not fully implemented and will throw an exception. This is different from how we'll handle iShape's methods. Continuing with our square class, here are the explicit implementations for the iShape interface, void iShape.draw, console.writeLine, void iShape.resize, console, writeLine, resizing a square. Again, notice the iShape prefix. Some important rules for explicit implementation. The syntax is return type interface name.method name. There's no access modifier, like public. These methods are effectively private to the class unless accessed through the specific interface. You can only access these methods through an interface reference. For example, you'd need to have an iShape variable pointing to your square object and then call draw on that iShape variable. Trying to call my square, draw directly on a square reference will result in a compile error if draw is only implemented explicitly. Let's see this in action in the main method. First, the circle. We create a circle and hold it in an iShape reference. Circle.draw outputs drawing a circle. Circle.resize outputs resizing a circle. This is standard implicit behavior. The public draw and resize methods of circle are called. Now the square accessed via iShape. We create a square and also hold it in an iShape reference. Square.draw outputs drawing a square. Square.resize outputs resizing a square. Even though square uses explicit implementation, because our reference square is of type iShape, the calls correctly resolve to square's iShape.draw and iShape.resize methods. Continuing in main, now let's access the same square object through an iShaper2 reference. This will call square's void iShaper2.draw method, which throws a not implemented exception. Square2.resize. Similarly, this throws a not implemented exception. This demonstrates that the behavior changes based on the interface reference type, thanks to explicit implementation. What if we try to call draw or resize directly on a square variable, mysquare.draw, compile error? mysquare.resize, compile error. As mentioned, because Square only uses explicit implementations, these methods are hidden from the Square class's direct public API. To call them, we must cast iShapeMySquare.draw. This correctly calls iShape.draw and outputs drawing a square. iShapeMySquare.resize outputs resizing a square. The key is that the interface reference iShape or iShape2 determines which explicit implementation is executed. This table provides a summary of the differences. Access modifier, implicit requires 1, like public, explicit forbids it. Name conflict resolution, implicit doesn't solve this if one method is intended for multiple interfaces with different logic. Explicit is designed for this, multiple implementations for same method name from different interfaces. Implicit uses a single method for all. Explicit allows per interface implementations. Rule of thumb, use implicit implementation for most cases. It's simpler and usually what you want. Use explicit implementation when you have method name conflicts between interfaces or when you want to hide an interface's methods from the class's direct public API. So, when exactly should you opt for explicit implementation? Name collision resolution. This is the classic case, like our iShape and iShape2 both having draw. Explicit implementation lets you provide separate logic for each. Interface-specific logic, you might have methods that are conceptually similar but need to behave differently depending on the interface's perspective. For example, iShapeDraw might draw to a screen, while an iPrintable if it existed, might prepare data for a printer. API cleanliness. Sometimes an interface requires methods that aren't core to your class's primary functionality. Explicit implementation can hide these from the class's direct API, keeping it cleaner and more focused. Forced interface usage. By making members explicit, you can guide users of your class to interact with it through its interfaces, promoting a more contract-based programming approach. Avoid explicit implementation if none of these apply, as implicit is generally simpler to use and understand. Now let's look at a slightly different scenario with our books example. This example will demonstrate interfaces, abstract classes, and inheritance working together. We'll have two interfaces, iControl and iDelete, both of which will happen to have a paint method. We'll then have an abstract class called textbook that implements both these interfaces. It will declare some abstract methods that derived classes must implement, and it will also provide an explicit implementation for iControl. Paint, finally, a concrete class, ScienceBook, will inherit from textbook and provide the specific implementations. The goal is to see how different paint methods are called, depending on how we reference the ScienceBook object. Let's start with the interface definitions for our books example. First, we have internal interface iDelete. This interface defines a contract for objects that can be deleted and painted. It has two methods, void deletes, void paints. Next, internal interface iControl. This interface defines a contract for objects that can be painted or controlled. It has one method, void paint. Notice again, both iDelete and iControl define a method named paint. This is a deliberate setup to explore how a class implementing both can handle this, leading us again to the utility of explicit interface implementation. Now look at the textbook class. It's an abstract class that implements both iDelete and iControl. Abstract public void delete. This is an abstract method. Textbook doesn't provide an implementation. It mandates that any concrete derived class, like ScienceBook, must provide it. This will serve as the implicit implementation for iDelete.delete. Abstract public void paint. Another abstract method. This will serve as the implicit implementation for iDelete. Paint via derived classes, key part iControl.paint. This is an explicit implementation of the paint method specifically for the iControl interface. This method is hidden from normal class usage and can only be called if you have an iControl reference to a textbook or derived object. Zoc textbook and its derivatives will effectively have two paths to a paint method, the abstract paint, which ScienceBook will override, and the explicit iControl.paint. Next, we have ScienceBook, which is a concrete class inheriting from textbook. Override delete. ScienceBook provides the concrete implementation for the abstract delete method from textbook. Here it sets the color to an empty string. This fulfills iDelete, delete, public override void paint. ScienceBook also overrides the abstract paint method from textbook. This implementation prints the book's color and will be the one called through an iDelete reference or a direct ScienceBook reference. Remember, ScienceBook also inherits the explicit iControl.paint implementation from textbook. Let's see how this behaves in main. iDelete new ScienceBook. We create a ScienceBook object but store its reference in an iDelete interface variable T1. What can T1 do? It can call delete and paint as defined in iDelete. It cannot access the color property directly because color is not part of the iDelete interface. D1.paint. This calls the paint method overridden in ScienceBook, the one that prints book color is. This is because iDelete paint is implicitly implemented by textbook's abstract paint, which ScienceBook overrides. Initially, color is null, T1.delete. This calls the delete method overridden in ScienceBook, which sets color to an empty string. D1.paint. Called again, it still invokes ScienceBook.paint, now with color as an empty string. Now, how do we call the other paint method, the explicit one for iControl? iControl control ref T1 as iControl. Or iControl T1. We take our T1 object, which is a ScienceBook, and cast it to an iControl reference, controlref.paint. Now this calls textbook.icontrol.paint, the explicit implementation. The output is controlled paint. iControl T1.paint does the same thing. Let's compare how the same object behaves with different reference types. ScienceBook directref new ScienceBook, directref.color blue, directref.paint calls ScienceBook.paint, shows blue. Delete ref.paint shows blue. iControl control ref2 directref control ref2 paint calls textbook.icontrol.paint, shows controlled paint. So what are the key takeaways from this book's example? When you call paint using an iControl interface reference, the explicit iControl.paint implementation in textbook is used. When you call paint using an iDelete interface reference or a direct ScienceBook reference, the overridden paint method in ScienceBook is called. This powerfully illustrates polymorphism. The interface type you use to view an object can determine which specific method implementation gets executed. A ScienceBook reference can call its own paint and delete and access color. An iDelete reference can call paint, the ScienceBook override, and delete, but not color. An iControl reference can only call iControl, paint, the explicit one from textbook, and cannot access delete or color. Remember, explicitly implemented methods require an interface cast for access. And just to reiterate why we'd go through the trouble of explicit implementation, as we discussed with the iShape example and see reinforced here, it solves name collisions when multiple interfaces have methods with the same signature. It helps avoid interface pollution by not forcing every interface method into the class's direct public API. It allows for conflicting or different implementations for the same method name tailored to specific interface contracts. It promotes clean separation and can encourage consumers of your class to use interface contracts.